So welcome. So we're going to talk today about getting my pen going. We're going to talk today about that's also interesting. We're going to talk today about conservation of energy, and for conservation of energy, we need to talk about isolated systems. They mean no friction, and non-isolated systems mean there's friction. And then we have a couple of other things. We have power and instantaneous power, and then power conversion. So there's like two main bits to it. Really three, because these are two distinct systems. So why this terminology? If you have a system and so here's mechanics and here's thermodynamics. And, you know, for a long time, people didn't realize they were connected. And then along came Joule, who said they're really two aspects of the same thing. But it's easy to think of them as separate things because they kind of behave kind of differently in many obvious ramifications. But there is a way that you can get energy to go from the mechanical system to the thermo system, and that's by friction. If you just rub your hands together, then you can feel the heat being generated. You're doing work overcoming the force of friction, or moving against the force of friction, and that work is converted into heat. Going the other way from a thermodynamic system into a mechanical system, that's a heat engine, which we'll get to, which we'll get to in thermodynamics at the end of the course. So when we say isolated, we mean to say, oh yeah, those guys all by themselves, and this wall is not crossable because there's no friction. And when we say a non-isolated system, we mean to say, oh yeah, there is a way of getting through because of friction. So it's two ways of saying the same thing. And another way of approaching it is if there are conservative forces or non-conservative forces. And what I want you to get across is that the non-conservative force, that means it does not... for non-conservative forces, the work done depends upon the path taken in moving between the initial and final states. So as you grind your way around the countryside, you know, the amount of work you do depends upon how far you actually slide. Well, that's a frictional effect. And there are other forces, but, you know, if you go up, what you pay in going up, you get back on going down, which is why we only care about the initial and final states. So when the absence of friction, for stuff like gravity and springs and electrostatics, I don't care about the path taken. I only care about the initial and final states. With this, over in friction, it's not just the initial and final states, it's the whole path taken that matters. So we talk about frictional systems being not isolated, and we talk about non-frictional systems as being isolated. Going back to our previous slide. Isolated. So, different languages. So, what's going on? Well, for an isolated system, what we say is that our mechanical energy is constant. And we say, well, then our kinetic energy... our change in kinetic energy, our change in potential energy of gravity, and our change of spring potential energy is zero. There's no change. This one might get bigger, but that one gets smaller, and this one stays the same. I mean, as long as the total amount is constant. It's like having a bank account with three different, you know, you might have checking, savings, and, I don't know, super savings or something. And you basically, you're not taking money in or out your bank account, it's just dancing around in there. That's an isolated system. On the other hand, when you have a frictional force, you're basically spending money. It's leaking out. It's going from your bank account to my bank account. So then we can't say that this is constant. There is a change. We can't say that EM is constant. There is a change in mechanical energy. So then over here we say, well, our change in mechanical energy plus our change in work equals zero. It's still, you know, there's that old adage about energy is neither created nor destroyed, but it is converted, you know, and in this case it is converted into work or out of work, etc. So Now the trick with this is, and I'll just warn you up front, is, so we could say my final energy, I could say my initial energy is equal to my final energy plus my work. And it turns out that because you're working against friction, work comes out as a negative thing. You're moving in that direction. Friction is pushing backwards. So work in this context will have a negative value. And so we put the work on that side. And we'll get to that in a minute. It's just a little, you've got to be careful about where you write that equation. So let's remind ourselves, we have kinetic energy, and that's a half mv squared. We have potential energy of gravity, which is mgh. And we have spring potential energy, which is a half kx squared. Yeah. So then we turn around and say, okay, student plots a graph of kinetic energy versus spring versus speed. So Ke versus speed. Which trace would she see? So can you do that one for me, please? So UK is upwards and speed is horizontal. So write down the equation and then double, bold the two parameters. So bold the two parameters so that you can see exactly what you're plotting, and then look and say, what kind of expression is this? And I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I got 28 people, so let's try and get at least 20. So write down the expression for, this is going to involve kinetic energy. And then my tip is you make whatever's on the y-axis, you write it in bold so you can see it in the equation. And then whatever's in the x-axis, you write it in bold so you can see what's in the equation. And then you say to yourself, what kind of expression is this in terms of those two parameters? And I'm going to just pause that for a minute because it's... So we're back and getting ready to stop this. So let's stop it and let's see what people said. Oh, mainly E, little bit of C. Let's have a look. So what I do on these is I turn around and write down my expression. K is equal to a half mv squared. Now, I can't bold, I suppose I can. I look at this side and it's K, so I'm going to bold that. And then I bold the V. Not the V squared, I bold the V. And so I can look at that and say, oh yeah, that's going to be that guy. Because I can see it. Now, supposing I can't see it, what do? You simply go down, you put a thing of K versus V, and you say to yourself, well, which is the independent variable? In this case, that's the speed. That's the thing I can adjust. So we'll go 0, 1, 2, 3, 4. And then I say, well, what happens about the K? And I'm just assuming that everything else is 1. So a half m is 1 because it makes my life easier. It's not going to change. So just call it 1. And then I say, well, if V equals 0, what's V squared? It's 0. And if V equals 1, what's 1 squared is 1. When V equals 2, what's 2 squared is 4. V equals 3, 9, 16. So this is K, and this is V, and then just there's my slope. So it's nice if you can see it just from the expression. It's also nice if you can plot it. And later on, I'm going to set you some problems where I don't give you 5 traces. I say, here's a graph, plot it. And people come back and say, but what numbers do I use? And I say, yeah, you're the engineer. You figure it out, And basically, it's not that there's a right set of numbers, but there's a right ratio of numbers. So depending on what you choose, you might have this going as 1 to 4 to 9, or you might have done it where it's 2 to 8 to 18, or you might have done it as 10 to 40 to 90. But there's a ratio there. There's a ratio as you look to those things, and that's what I look for. Most common mistake is people, they don't do this. And they go, oh yeah, half mv squared. So, well, we got, let's have a look, we have ke, and we have, v squared. So that's going to be linear. So they say it's linear because the equation has a k and it has a v squared. And they don't recognize that they're not plotting v squared. They're plotting only v. And so they go, well, yeah, that equals that. Everything else is constant. And that's not true. So you've got to slow down a little bit. Student plots gravitational potential energy versus height. So this is, well, let's do that. Let's do that. Do that for me, please. We're back. And let's stop it here and see what people say. Pretty well everybody's saying D. You go UG is equal to MGH, and again you put in bold, I got U as one of my axes and I got H as the other axes, and so I can see that's linear because the MG is not going to change. Or I could ask you to plot UG versus H, in which case you'd go, well, let H equal 0, 1, 2, 3, and then you go, well, let MG equals 1, just like we said a half MV equals 1. And we say, okay, when that's 0, that's 0. When that's 1, that's 1. When that's 2, that's 2. That's 3, that's 3. And then we plot our UG versus H, and we go 0, 0, 1, 1, 2, 2, 3, 3. Oh, yeah, look, it looks like that. So, and then student plots a graph of spring potential energy. So my US is equal to 1/2 kx squared. So again, I can see that there's my y-axis, and my x-axis is just that. So that again is going to be that guy. And so if I want to just plot the graph out, I would go x 0, 1, 2, 3, 4, and so that'd be 0, 1, 4, 9, 16. And so on. So there's the scale. Okay. Block moves because it has a kinetic energy of 14 joules. How much kinetic energy would another block have if it had 3 times the mass and moved at twice as fast? This is the ratio problem. So remember about how we do ratio problems, and I want you to do that, please. Okay, we're back. So let's stop this and let's see what people are saying. People are saying, oh, mainly E. So let's see how that goes. So you recall. So the first step in this is you recall the equation, and the equation for kinetic energy. So K is equal to half mv squared. So what you do is you put K new over K old. And I don't know the K new, so I'm going to put that down, but I do know the K old because it says the kinetic energy was 14 joules. And that's the step that people sometimes just skip. And that equals 1/2 m nu v nu squared over 1/2 m old v old squared. And now I'm doing sums. It's a half and a half. That's going to go away. And then it says that it has 3 times the mass. So that's going to be the new one is 3 and the old one is 1. And then it has twice as fast. So the old one is 1 and That one's 2. And then we've got to square both of those. So we're going to say k nu over 14 is equal to. And, you know, it's worthwhile slowing down a bit here because, you know, you don't want to just make a slip on that. Those guys go down, those guys go down. And this equals 3 times 4 over 1 times 1, which equals 12 over 1. So K nu is equal to 12 times 14, which equals 168. Once again, please, I'm having trouble because people are talking and I'm having to talk over you, so please stop. Okay? So there it is. The most common mistake is people put down the 12 because they're not writing incomplete sentences. They kind of know it's the ratio and they do, probably they start here and they do that bit. And so they end up with an answer of 12 and they put down the answer of 12 and they're on to the next question, ignoring the fact that you were told that the original one was 14. I'm not asking for the ratio, I'm asking for the new value. So watch out for that. And then the other thing I'd say sometimes is people, they're not even using the ratio. They're just putting down, well, it's a half mv squared, and then they're trying to do the ratios in their head. And, you know, I don't do it this way because it's somehow virtuous. I do it this way because I want to get it right. And if I got it right as often by just putting a few numbers down, that's probably what I'd do. But yeah, I'm not trying to teach you here. I'm letting you look over my shoulder as I try and get them right. So just remember that. I'm your coach and I'm saying you need to, you know, try this. And if you do better doing it another way, then maybe some, you know, new kind of methodology. But if you're not doing as well, then you've got to try this method because it works. So just watch out for that. Cool. And then we have this. So now, having reminded ourselves a bit about those energies, then let's talk about mechanical systems. We're going to talk about isolated mechanical systems. So do isolated mechanical systems have friction or not have friction? Click A if isolated systems have friction, and B if they do not have friction. Let's fly through this. A if an isolated system does not have friction, and B if the isolated system has friction. A, no friction. B, friction. So what's going to be? It's going to be stop. So let's look what people say. So mainly A with a little bit of B, and the answer is isolated systems. Remember what we said? We said that we have our mechanical energy world and we have our thermal world. And an isolated system is just like that. There's no thing to thermal, so there's no need for friction, so it's no friction, so it's A for that one. So these have no friction, and these here, you can see it, rough snow. These are friction. Okay, cool. So typical examples, pendulums, roller coaster rides. We have exotic roller coaster rides like railroads going through mountains and stuff like that. Let's just talk about the principle to begin with. So a pendulum. Pendulum is an isolated system. We ignore the air resistance. We ignore the friction at the bearing of some kind. We just got a mass suspended by a massless piece of string. And we say a pendulum swings from A to B to C. So A to B to C. It's going to go further because it's going to be symmetrical, but I'm only interested in the A to B to C bit. At A, it has a UG, gravitational potential energy, so UG is equal to 7 joules. And a K is equal to 0 joules. So I know it's at the end of the swing at A. At A, it's at the most extreme point because it stopped moving to the left and it started moving to the right. So, okay. And also from this, so it's asking me what is its mechanical energy. And I know that my E mechanical equals my kinetic energy plus my UG plus my US. There's no spring here, so I'm not even going to bother about that. So my EM is equal to literally my 0 plus my 7. So my EM is equal to 7 joules. So it's basically just visualizing like that.
What is there in the US?
I'm sorry?
Oh, it's fine.
I'm sorry?
I just asked about the US.
About the US? Oh, US, U spring, yeah. It's just, it's part of the mechanical energy family, but there's no spring here.
And so if it doesn't have anything, you don't have to find it. Like if it doesn't have one of those three.
You don't even have to write it down. It's kind of good if you do. And again, please, please, please. Okay. So, next, you do the next one. I'm going to put you on pause. So let's have a look. Almost there. Good, 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 good. So we'll look at this and we're going to say, okay, yeah, pretty well everybody's saying C, so let's just confirm that. So we're going to say, okay, so my mechanical energy is equal to my kinetic energy plus my gravitational plus my spring, and I don't have a spring in this case. And what do I know? Well, I know it's the same question, so I know that my mechanical energy, we just calculated it, is equal to 7 joules. And at the bottom is what I'm trying to find, so that K is what I've got. And then I know that this is the lowest point. And so I know that my potential energy is 0 on this. And so I say, well, okay, so K is equal to 7 joules. So it's C on that. Yeah. Now, how did you know that it was 0 joules at the bottom? Well, what else can it be? I mean, if you're not, where are you measuring from if you're not measuring from the bottom of your pendulum? Now, that's not spelt out, but again, we're not lawyers. If we were lawyers, then we'd spell it out. But we're physics people, we're engineers, and so we know that we have to measure from some relevant point. I'm measuring my velocity with respect to the room that the pendulum is moving in. I'm not measuring it with respect to Saturn. So I'm making an assumption about where I start my 0 velocity. So I'm making an assumption about where I start my 0 in my height. And, you know, that contextually makes sense. Yes?
So I don't understand. Why is the gravity 0?
The UG?
Yeah.
Because you measure it relative to the bottom of the pendulum. So if this equals mgh, h is measured upwards. So if that's 0h, that's 0. Yeah, cool. And then this last one. So here's an interesting one. It's point C, which is a little bit of both. So I have to go at that one, please. Let's have a look. So let's stop there. What do most people say? Most people are saying solidly B. So let's have a look at that. And we say here is, again, we same methodology. So we say our mechanical energy is equal to kinetic energy plus our UG plus our US. And I turn around and say, well, it's always 7 because its mechanical energy is constant in a isolated system. And my kinetic energy, I'm told, is 2. So plus UG. So UG is going to equal 7 minus 2, which equals 5 joules, which is that guy. Cool. So simple sums. And we're not. This is not a test question. This is just principle to get you going. Is a nice frictionless roller coaster. Bottom of the track. At point A, which is the top of the track, the block has a kinetic energy of 4 joules and a gravitational potential energy of 8 joules. So 3 questions on that. Let's have a look. The first one, I'm going to get a move on because we're going a bit slow. So the first one, I'm going to say, well, what's it called? EM is equal to K plus UG plus US, and there's no spring involved. So then my EM is equal to my K, and I'm told that's 4 plus my UG, which is 8, which equals 12 joules. So that's pretty well set, yeah? Agreed? And then we can do, and we go, well, EM is equal to K plus UG plus US, and there's no US. And it says at point B, there's point B. Point B, UG is only 3 joules, so this means that 12 is equal to K plus 3 joules. It was 8, but now it's 3. So that means that K is equal to 12 minus 3, which equals 9 joules. So B again. And then at point C, here's point C, I've gone raised up again. I say EM is equal to K plus UG plus US. And I know EM's always 12, but I know in this case that my K is 5 plus UG. So then I know that UG is equal to 7 joules, which is that. Cool? Agreed? So just bookkeeping, yeah. Because there's no friction.
At D, would its UG be 0?
UG, why would on B UG be 0?
Is that where you're like measuring it from?
Well, clearly, no, not because on UG, I say UG is 3, so...
At D.
At D, I'm sorry. It may or may not be. All I'm telling you is... so you raise a good point. So it turns out it need not be, because I could have my roller coaster ride starting here. Okay? But with the pendulum, you can't go lower than the bottom of the pendulum. So the tradition is we call that 0 in our math. Yeah, cool. Good point. Pendulum swings out. So this is the next level, and this is going to involve a bit more math. So pendulum swings out 30 degrees. So you know that this guy here is 30 degrees. And for the vertical axis, the pendulum is 2 meters long. 2 meters long. So that's going to be 2 meters. And this bob is 4 kilograms. Bob is the mass on the end. It's just called bob. I have no idea why it's called bob. It's like a plumb bob, you know. It's like just called bob. What is its speed at point B? So I want to know my, depending on which way it goes, doesn't matter. It's just my speed at point. I want to know that guy. So first thing I do is I recognize it's an isolated system. So it's an isolated system. Because I'm given no information about friction, so I got to assume it's isolated, or else I can't do the problem, and no one can do the problem. So it's an isolated system, and then I say, well, in an isolated system, then my mechanical energy is equal to my well, I can say my change in mechanical energy equals 0. So I can say that my change in my kinetic energy plus the change in my gravitational potential plus the change in my spring potential equals 0. There's no spring potential.
Why does the mechanical equal 0?
Because it's an isolated system. If it's isolated, there's no losses due to friction, and there's no energy coming in from the outside because it's isolated.
Were the previous questions isolated?
Yes, they were all isolated because we added up all the energies and they always equal the same amount of mechanical energy. So then I can say, well, okay, I can express this. Let's just express this in a bit more convenient form. So I can say, oh, in that case then, my kinetic energy initial plus my gravitational energy initial is equal to my kinetic energy final plus my gravitational potential energy final. Does that make sense? Yeah, just initial equals final, because there's no change.
Go back. Yeah.
So then I can say, well, that means that a half m V initial squared plus mgh initial is equal to a half mv final squared plus mgh final. Okay, so I'm going to say my final position, well, it doesn't matter which way around I do it, so I'm going to imagine this. I'm going to say that this is my initial position and this is my final position. And so I want a half. I'm going to leave the m's in it because everything has m in it, so it's all going to cancel. And then v initial squared, that's what I want to find out. Plus, and again, it's a pendulum, so I'm going to call this m times g times 0 because that's my 0 level.
Is that MIF?
Velocity initial, mass time, oh, sorry, that should be squared. Sorry, thank you. That should be squared. So mass initial, velocity initial squared plus mg, and that's going to be 0, is equal to, now I'm looking over at this side, I'm looking here at this final position, and I know that's 30 degrees, and I know that's 2 meters. And I know that at that point, because it swings out 30 degrees, it has no speed. So this will be a half times m times 0 squared. Because here, my v equals 0 meters per second. Here my h equals 0 meters. And here my v equals 0 meters per second. Because it swings out 30 degrees. No more, no less. So then I have plus the mass of this thing times g times h final.
Would that be 2?
Now, if you look at it, look at your diagram, that's 2. And there's the h I want. And just by looking at it, can you see, is that 2 meters? It's clearly not, is it?
No.
So that's the rub in this question. How do you find that height? And it turns out it's one of these situations where the first time you see it, you're flummoxed for a while, and then you get it. And once you've seen it, you can always do it from then on. It's one of those. It's like a joke or a crossword puzzle clue where it flummoxes you, and then you go, oh yeah, got it. And so that's why, in a way, I like to show you these things before. I think it's a useful thing to have, but I'm not going to be trying to test your aptitude for solving puzzles. I want to test your ability to do physics. And so I don't mind showing you this, because then you have access to it. And, you know.
Why is the velocity 0?
Can I just finish? So basically what I'm going to do is I'm going to try and find this height here, okay? And so how long is it from the very top to the very bottom? It's a piece of string, isn't it? And it doesn't stretch. So I can say, let's just put it algebraically. So my L is equal to h dash plus h. And my L equals 2. And what does h dash equal in, give me a trig term for my h dash.
2 cosine 30.
It's going to be 2 cosine 30 plus h. So that means that my h is equal to 2 minus 2 cosine 30. And so we take out our handy-dandy calculators. So I'm going to check, I'm on degrees, and I go 2 minus parentheses 2 cosine 30 parentheses, whoops, not 9. It's the, let's do that again. So it's 2 minus parentheses 2 cosine 30 parentheses, and that's going to be 0.2679, call it 0.27, 0.27. Okay. So now I come back up to my thing here, and I say half times m times vi squared is equal to 0 plus m times 10 times 0.27. Now, you can put m in if you like, but I might not give you m because you don't need it. So I can say, well, the m's go away. Let's do that in a different colour so we don't get confused about why the m's go away. So let's have a look. Ink, let's do that in black. So those m's go away because they're constant throughout. And then let's go down here. So then I turn around and say, okay, so vi squared is equal to, it's going to be 2.7 times 2, which took the half to the other side, and it becomes times 2. So that becomes 5.4. So vi is equal to the square root of 5.4, which equals, okay, here we go, second square root 5.4. It's going to be 2.32. And that's going to be meters per second. So it's same principle, slightly different geometry, a bit more math involved. But that's the game I can play. The game I can play is I don't tell you the potential energy. You work the potential energy out. So do you know mgh? And I don't tell you the kinetic energy. You work the energy out. So you do a half mv squared. You still got to know that the energy initial equals the energy final. You still got to know that the mechanical energy is constant. So it's a level off from those previous questions. Much more like a test question. Okay. Yes. Question or comment?
Why couldn't the height for the MGH2 just be 2 meters since it's just straight?
I didn't catch that last bit. Why couldn't the height for the MGH2 final, you mean?
Yeah, fine.
Yeah. Why couldn't it be?
Why couldn't it just be 2 because I like the string?
So, yeah, where's this bob end up? It ends up at that point there. Didn't end up all the way up there. Ended up at that point there. Because it says it swings out 30 degrees, yeah? So then that height is that height, and it's not that height. It's not the whole thing. Yeah. If it had gone 90 degrees, it would have been 2. So see, you got to project it across. Yeah. Go. That's the most common mistake. People put 2 in because it's like, oh yeah, it's a height. You gave me a height. And again, that's why if you're not drawing diagrams, you will lose out on points quite often because it's all about the visualization. The math here, we can all do this math. It's all about the visualization. It's not height, it's which height are you going to use. That's really what it's all about. I want to do one more. So I'm going to go and, I've got to do this thing, haven't I? So I'm going to put this on pause so that the people at home don't have to